Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating area. Can theoretical physics research benefit from language agents?
That's a big question. Theoretical physics is already pretty abstract and complex. So throwing AI into the mix, it's either going to be revolutionary or a complete mess. I'm leaning towards revolutionary, personally.
I'm a bit more skeptical. While I see the potential for language agents to help with certain tasks, like sifting through the massive amounts of research papers, I'm not convinced they can actually contribute to fundamental breakthroughs. We need to be very careful about overhyping these things, you know?
I think it depends on what we expect them to do. If we expect them to magically solve the standard model, then yeah, disappointment is likely. But if we see them as tools to assist physicists, especially in areas like handling complex mathematical relationships and translations between coordinate systems, then I think there's real potential. Theoretical physics is built on math and translating between different representations of reality. So, it's all about that.
Right, exactly. It's not about replacing physicists, but augmenting their capabilities. And I think the recent advances in language agents, particularly when combined with neuro-inspired algorithms, open up some exciting possibilities. Like imagine a language agent trained on the entirety of theoretical physics literature, capable of identifying patterns and connections that humans might miss.
Oh, absolutely. Think about it. There are so many papers published every year, even the most dedicated physicist can't keep up with everything. A language agent could act as a super efficient literature review, pointing out relevant papers, summarizing key findings, even suggesting potential research directions. It would be like having a team of research assistants working 24/7.
That's true, the data management aspect is definitely appealing, but I still worry about the black box nature of these models. If the language agent suggests a research direction, how do we know it's not just based on spurious correlations? We need to be able to understand why the agent is making those suggestions, not just blindly follow its recommendations. Explainability is key.
And that's where the coordinate system translation aspect comes in. Think about different ways of formulating the same physical law. Newtonian mechanics, Lagrangian mechanics, Hamiltonian mechanics. They're all saying the same thing, but in different mathematical languages. If a language agent can understand and translate between those different representations, it could potentially reveal deeper connections and symmetries that we haven't fully grasped yet. It's not just about finding correlations, it's about understanding the underlying mathematical structure.
That's a fantastic point, Donald, and it aligns with some of my recent thinking. The very act of a language agent parsing the complexities of theoretical physics might reveal unexpected parallels with how the human brain handles abstract concepts. It's like by trying to mimic the thought processes of a physicist, we might gain insights into the architecture of the brain itself.
I like that. And it's not just about the brain. Think about the potential for language agents to identify missing pieces in our theoretical understanding. Like, maybe there's a subtle mathematical inconsistency in our current model of dark matter, something that's been overlooked for years. A language agent could potentially flag that inconsistency and point us towards the missing piece of the puzzle. It could actually help us find new physics.
But isn't that just wishful thinking? These language models are trained on existing data. They're not going to magically come up with new physical laws that haven't been discovered yet. They can only regurgitate and remix what they've already learned. We need fundamentally new algorithms, not just bigger datasets and more complex neural networks.
I agree that we need more than just brute force deep learning, but I think the ability to translate between different coordinate representations is a crucial piece of the puzzle. Imagine a language agent that can represent the same physical phenomenon in terms of, say, both quantum mechanics and general relativity. Even if it doesn't understand the underlying physics in the same way a human physicist does, its ability to manipulate those different representations could potentially reveal inconsistencies or hidden symmetries that point towards a unified theory. Current deep learning mostly does pattern matching, not true understanding or translation.
Right, and that's where neuro-symbolic approaches come in. It's about combining the pattern recognition capabilities of neural networks with the symbolic reasoning of traditional AI. If we can inject well-defined algorithms and constraints into these language models, we might be able to bridge the gap between the black box nature of deep learning and the more structured knowledge representation of symbolic AI. The tracker injection paper touches on this, injecting algorithm-specific knowledge into LLMs.
That's interesting. So, instead of just feeding the language agent raw data, we're giving it pre-packaged algorithms, like little building blocks of knowledge. That could definitely improve its ability to reason and make more meaningful suggestions. And it would also make it easier to understand why it's making those suggestions, which addresses Sarah's concerns about explainability.
Okay, I'm willing to concede that a neuro-symbolic approach is more promising than just relying on deep learning alone. But I still think we need to be very careful about how we design these algorithms. We need to ensure that they're based on sound theoretical principles, not just on statistical correlations. Otherwise, we're just building more sophisticated versions of the same black box.
And that's where the spatiotemporal reasoning comes in. Theoretical physics isn't just about space, it's about space and time. And different theories treat space and time in different ways. A language agent that can understand and manipulate those different representations of space-time could potentially offer valuable insights into the nature of reality. Imagine it could translate between the classical space-time of general relativity and the quantum space-time that might emerge from string theory. That could be huge.
Exactly. And think about the potential for language agents to accelerate the translation of neuroscientific insights into new computational models of thought processes. We can train these agents on massive amounts of neuroscientific data, and then use them to generate AI architectures that mimic the way the human brain handles complex concepts in physics. It's about creating a cognitive scaffold for designing more biologically plausible algorithms.
The idea of a cognitive scaffold is really powerful. It's like, instead of trying to build AI from scratch, we're using the human brain as a template. And theoretical physics, with its abstract concepts and complex mathematical structures, is a perfect testing ground for these types of algorithms. If we can build AI that can understand theoretical physics, then we're well on our way to AGI, right?
Wow, hold on a second. AGI is still a long way off, if it's even possible. And I think it's dangerous to equate understanding theoretical physics with achieving general intelligence. Those are two very different things. Just because an AI can manipulate equations doesn't mean it understands the underlying concepts in the same way a human physicist does.
But even if it doesn't have human-level understanding, the ability to manipulate those equations and translate between different coordinate systems could still be incredibly valuable. It could lead to new discoveries and new insights that we wouldn't have been able to achieve on our own. It's like having a super-powered research assistant that can handle the grunt work and free up physicists to focus on the more creative and intuitive aspects of their work.
And the potential for discovering fundamental physical principles is huge. Language agents can analyze vast amounts of theoretical physics literature and identify patterns that might be missed by humans. Plus, this data also could train language agents tuned for the field. It could revolutionize the search.
Exactly. I mean, think about the sheer volume of data that's out there. There are centuries of theoretical physics research just waiting to be mined. A language agent could sift through all of that data and identify key concepts, summarize important papers, and even point out connections that have been overlooked. It would be like having a team of historians and physicists working together to uncover the hidden history of the universe.
Okay, I'm starting to see the potential. But I still have reservations. I'm worried that we're putting too much faith in these algorithms and not enough emphasis on human intuition and creativity. We need to remember that AI is just a tool, and it's up to us to use it wisely. We can't just blindly follow its recommendations without thinking critically about the underlying assumptions and limitations.
And we need to be careful about how we train these algorithms. If we train them on biased data, they're going to perpetuate those biases. We need to ensure that the data is representative of the diversity of perspectives and approaches within theoretical physics. Otherwise, we're just going to end up with AI that reinforces the status quo.
That's a crucial point. Bias in data is a huge problem, especially in fields like physics, where certain voices have historically been marginalized. We need to be proactive in addressing those biases and ensuring that these language agents are fair and equitable. So let's summarize. Where should future research focus?
From my perspective, I'd like to see more research into how we can structure and tag datasets in theoretical physics to make them more accessible to language models. We need to develop new types of knowledge graphs that can capture the complex relationships between different concepts and theories. The structure, especially in fields like quantum mechanics or general relativity, needs a more sophisticated symbolic representation than simple textual descriptions. I am curious as to whether language models trained in this way can begin to fill in the gaps in our understanding, hinting at the nature of reality, but only more data can answer that.
I think we need to focus on developing more robust neuro-symbolic algorithms that can effectively combine the strengths of both symbolic and connectionist representations of knowledge. We need to move beyond brute force deep learning and start building AI that can actually reason and understand the underlying principles of theoretical physics. In particular, I'd be interested in seeing how we can leverage symbolic AI to handle the complex equations and variable structures that are so common in theoretical physics. We need to create better foundations of knowledge representation.
I think the key is to develop algorithms that can seamlessly translate between different coordinate systems. A critical aspect for language agents to truly aid in theoretical physics would be their ability to articulate and manipulate abstract mathematical objects within these different coordinate frameworks. That's what opens the door for true spatiotemporal reasoning and a deeper understanding of the relationships between different theories. And I'm curious to see how language agents can help us visualize and manipulate complex mathematical structures, especially those involving multiple dimensions in time.
And from my perspective, I'm really interested in exploring the potential for language agents to act as a bridge between neuroscience and AI. We can leverage pre-trained language models to better understand and model the neural mechanisms underlying cognitive processes, particularly those related to decision-making and planning. And I think the idea of tracker injecting algorithm-specific knowledge into language models, is a really promising direction for future research, helping to align AI algorithms with the principles of biological intelligence. Also, seeing how language agents trained on theoretical physics will reveal insights in the brain itself and how we can create a cognitive scaffold for intelligence.
Those are all fantastic points. It sounds like we all agree that language agents have the potential to revolutionize theoretical physics research, but we need to be careful about how we develop and deploy them. It's not about replacing human physicists, but about augmenting their capabilities and accelerating the pace of scientific discovery. But I think language models might have a hard time with tensor equations, for example, and that is a very deep and wide part of physics.
Exactly. It's about using AI as a tool to help us explore the universe, not as a replacement for human curiosity and ingenuity.
And it's about ensuring that those tools are fair, equitable, and transparent.
Well, that's all the time we have for today. Thank you for joining us on Cognitive Spirals. We hope you found this discussion thought-provoking. Until next time, keep exploring.